Okay, after completion of different laws of thermodynamics, different processes like adiabatic, isothermal, isobaric, isochoric, reversible process, irreversible process, and the discussion on heat engine, then refrigerator, then heat pump, then finally a cyclic process, and then uh, reversible, irreversible process, and then discussing about the Carnot engine, okay, which is a completely reversible engine with ideal gas as the working substance. We derived the efficiency of Carnot engine. We have derived the efficiency of a heat engine and the coefficient of performance of heat pump. And we told that efficiency of heat engine can never be equal to 1. Coefficient of performance of a refrigerator can never be equal to infinity. And same thing, that is the second law of thermodynamics actually. You have to throw some heat to the surrounding. You cannot use completely, work cannot be converted, heat cannot be converted to work. So that was second law of thermodynamics, and first law of thermodynamics was conservation of energy. Okay, so we have, and then we have derived the work done for isothermal process, for adiabatic process. Using the work done principle, we have derived the efficiency of Carnot engine. Okay, so all these things we have covered in last few days. Okay, so now today we'll summarize what we have studied in last few days, and we'll try to solve some typical numericals which will cover almost most of the things that we have done. Okay, so I'll try to summarize what we have studied. Okay, so first is we have studied first law. Okay, okay. Oh, we have studied first law. Okay, so first law says del Q is equal to del U plus del Y. That is conservation of energy. That is first law of thermodynamics. Okay, and that is one important thing. And one thing that was bit theoretical, that is related to in your chapter, that was mentioned at say specific heat capacity. Okay, during that discussion, one important thing was derived that we have not covered. That is called, like, let us say, that is called Cp minus Cv is equal to R. Okay. I have explained you Cp minus Cp by Cv is equal to gamma. Okay. But there is another derivation that we have not done. You can refer it actually. It was a bit theoretical, so that's why I have not derived. Cp minus Cv is equal to R. Cp by Cv is equal to gamma. Okay. So Cp is, I told, specific heat at constant pressure, specific heat at constant volume, and specific heat is what? Specific heat is uh, specific heat is nothing but amount of heat required. Specific heat is amount of heat required to raise the temperature by unit by unity or unit mass of gas, mass of any substance. So that is of any substance. So that is specific heat, and we have said that specific heat, like if you are applying some heat, Q is equal to mCp mc delta T. Okay. So this C is nothing but Q by m delta t. So what we are saying that specificity is nothing but equal to q. So C is equal to q when m is equal to unit and delta t is equal to unit. Right? Yes. So that's why we are telling specificity is nothing but amount of heat required. Right? Specificity is nothing but amount of heat required. Amount of heat required to raise the temperature by unit. One. Raise the temperature by unit T or unit mass of substance. It can be anything, 1 kg or whatever, or unit it has to. So m and delta T will come to the numerical. So many times you need to know the unit of specificity. So Q has unit calorie, or it can be joule also. Calorie and joule, they are for heat and for work, they are used interchangeably. So to be consistent, we can say that if somebody asks you what is the unit of specificity, joule or kg or Kelvin. Okay. So that is the unit of specificity. And then you can find out the dimension also of specificity. So you know joule is nothing but work done. Work done. So work done is nothing but force into distance, right? Force into distance. Then kg is nothing but your mass, right? We are finding out the dimension, okay? Then Kelvin is your, this is, okay. So let us simplify the unit first, okay? So joule is like your force into distance. Then this is kg. This is Kelvin. Okay. So then now you know your force is nothing but, so your specific is equal to force into distance divided by kg Kelvin, right? Kelvin. So force is nothing but your Newton meter, right? Newton meter, because yeah. So force into distance is nothing but Newton meter. Newton into meter divided by kg into Kelvin. Okay, so then this Newton is what? No, we have to convert it to the basic fundamental units. Okay, so Newton is not a fundamental unit. Like you know, there are two things. One is SI and one is FPS. Okay, so in SI, what are the fundamental units in international system of units? SI is nothing but international system of units. So in SI, it or MKS, okay. SI is otherwise MKS. MKS is M stands for meter, K stands for kg, S stands for second. So you have to bring it to that fundamental things. So your Newton is nothing but meter per, like Newton is the force which will create 1 meter per second square acceleration in 1 kg of substance. Okay, so that's why Newton is kg meter per second square. Remember that. Newton is nothing but kg meter per second square. And then distance is your meter, right? Then your in the denominator you have kg Kelvin. Okay. So your kg cancels out. Okay. So it will be finally it will be meter square divided by second square. Okay. Meter square divided by second square into Kelvin meters. Okay. So that may be the final unit. Actually, if you see this, normally they will write it as a joule per kg Kelvin or whatever. But if you want to find a dimension, you have to go into the fundamental unit of M, L, and T. So there are three things: M, L, and T. Mass, length, and time. In terms of these things, like MKS, what is meter is length, kg is mass, this is time. So you have to always write when you go into the fundamental dimension, you have to write in terms of M, L, and T. So your what it has finally become, M means you have to write like L square, right? Because this is meter, right? A meter is nothing but length. Okay. So this becomes L square divided by T square into Kelvin inverse. Okay. So L square Kelvin inverse minus T square. Okay. So uh, uh, that's what the dimension here now for this thing. Okay. So that is what the dimension of specific it should be. Specific dimension is this and unit is this. So you need to remember the unit always joule per kg Kelvin. So that's the unit of specific heat. So you can always get numericals on a specific heat. And remember that Cp minus Cv is equal to R. R is nothing but your universal gas constant. I have already given you what is the value of universal gas constant, what is the unit of universal gas constant. All these things I have already taught you. You should remember it. What is the value of universal gas constant? Yes. So that it is very important to remember the value and unit of universal gas constant because everywhere you will be using it. Okay. So let me rub it. Okay. So we have. Uh, okay. Now then we have discussed about the work done in a isothermal process. So we have done it like this, like PdV, like that is the work done, and in a isothermal process, Pb is equal to constant. So we had done like work done in a work isothermal process is equal to PdV integration from V1 to V2. So we knew that isothermal process P into V, P in the y-axis, V in the x-axis, and it is going from state 1 to 2. So there is a infinitesimal process when infinitesimal area where this P can be assumed to be constant. So P assumed to be constant, this volume change is dV. So this is PdV. So that PdV, integration is nothing but area under this curve. So when you do integration and try to find the area under the curve, the volume goes from V1 to V2. So the integration lower limit is V1, integration higher limit is V2, and then P we have it is a constant. So we have written because you are integrating for volume, you have to write this term also in terms of volume. So this P becomes K by V. So you can replace P by K by V and then a dV, then V1 to V2. So after doing this, it has become K and V1 to V2, dV by V. Then it was like K, ln V, then V2 to V1. This is what the final outcome was. And finally, this K constant, you can write it as nu RT or whatever because it's a constant. Okay. So finally, we got the work done in a isothermal process. The work done in a isothermal process to be, we got nu RT, nu RT ln D2 by This has to be remembered. See, we cannot, in your type of exam, we always cannot derive things. So we need to write down the summary of all the formulas covered in the chapter. But it is essential to understand the theory behind it. If you understand the theory behind it, it will be very easy for you to remember the formula. So, but remember that, okay, this you have to remember this. There is because you are facing MCQ questions, so there is no other go without remembering the formula because you don't have that much of time to derive and do. Okay, so that is the work done. Okay, and then that is for isothermal. Okay, isothermal. This equation, then adiabatic. Okay, then adiabatic work done. Also, we have derived similarly work done in adiabatic to be nu r capital T1 minus T2 divided by gamma minus 1. Okay. So this you have to remember. No other. You have to remember this. Nu r T1 minus T2 divided by gamma minus 1. Okay. This is the work done for adiabatic process. So what happens in isothermal process? T remains constant. T constant. Whereas in adiabatic process, heat input del Q is equal to 0. There is no heat input. Like we say something is adiabatic wall. That means there is no heat transfer happening. So that is important thing. So T is equal to constant. That is isothermal thing. Del Q is equal to heat input or heat output is equal to 0. That is adiabatic thing. And work done is this much for your adiabatic. Okay. And we have discussed like this in adiabatic process, this gamma comes into picture. This gamma is nothing but your Cp by Cv. Okay. And always remember that Cp is always greater than Cv. That is important. So that's it. Because we are telling that Cp minus Cv is equal to R. Okay. If it is R is a positive number. So that's why Cp is always greater than Cv. So remember this. Cp is greater than Cv always. So the amount of heat required to raise the temperature of unit mass at constant pressure is always more than amount of heat required to raise the temperature of unit mass by unit temperature is always more. Okay, that needs to be remembered. So Cp minus Cv is equal to R. Cp by Cv is equal to gamma. Okay. Okay. Then uh, so So it is very much essential for us to solve any numerical. If they ask you what is the work done, and uh, if they ask you what is the work done in a isothermal process or adiabatic process, it is very essential that we remember. Uh, it is very essential that we remember these formulas. Okay. Then we have discussed about heat engine. Okay, in heat engine we have derived the efficiency. Okay, we have said okay, we have said efficiency is nothing but work done divided by heat input. Okay, right? So we have said how much is the work done in a heat engine. Like we know, work done is equal to del U bar plus del W. Okay. So as you know, in case of a heat engine which is going through reversible process, okay. Let us say my Carnot engine is an example of heat engine. My Carnot engine is an example of heat engine which is going through some reversible process like this. Okay. Okay. So if it is going through reversible process like this, that means it is going from 1, 2, 3, 4. So it is going from, like, it moves like 1 to 2, it moves from 1 to 2, 2 to 3, 3 to 4, then again 4 to 1. So because it is back to 1, that's why it's a reversible process, a cyclic process. So it's a cyclic process, that's why it will start with temperature T1 and end with temperature T1. That is the reason if the temperature remains constant at the beginning and at the end, that means there is no change in internal energy. That is important. There is no change in internal energy in case of heat engine. Okay. So if that is the case, then your del Q becomes is equal to del W. Del Q becomes equal to del W. Then what is del Q? Del Q means you are in the engine, like you have you have a source, you have a sink. Okay, so you have a source, you have a sink, you are you have a working substance, you are taking some heat, you are giving some heat, you are doing some work, right? You are taking Q1, you are giving throwing away Q2, okay, and you are doing work W, okay, you are doing work W, you are doing some work W, okay. So this from this your what is the net heat gain? That net heat gain is nothing but your del Q is equal to Q1 you are taking and Q2 you are rejecting. So del Q is nothing but your Q1 minus Q2. That is the net heat this working substance is gaining, that ideal gas or whatever it is. That is the net heat going to the working substance. So that is the del Q, net heat on the substance. So you know my efficiency instead of W, I can write it as I can write it as Q1 minus Q2 divided by Q1. Okay. So if I simplify it, minus 1 minus Q2 by Q1. Okay. So that is the efficiency. How much heat is getting rejected to the sink? How much heat is taken from the sink? So the amount of heat rejected, this is the efficiency of a heat engine. So because you are forced to reject some heat as per the law of nature, that's why efficiency cannot be 1. So in a case when Q2 is equal to 0, in that case your efficiency will be becoming 1. But you have to reject some heat as per second law of thermodynamics. That's why efficiency cannot be 1. So this 1 minus, so this efficiency is equal to 1 minus Q2 by Q1. You can relate it to Carnot engine, that will become 1 minus T2 by T1, just for remembering. So T2 is your sink temperature, T1 is your source temperature. That is for Carnot engine, not but for heat engine. This is the general efficiency equation. That is that is to summarize, that is the efficiency of this thing. And then we have discussed about coefficient of performance. So the way you talk about efficiency in case of heat engine, similar thing applies to your kind of your heat pump or the refrigerator. Okay. The only difference between heat pump and refrigerator is that in refrigerator you are concentrating on the inside volume of the refrigerator from where you are taking away the heat. But in case of heat pump, you are concentrating on the room which you are heating. So in case of refrigerator, you are concentrating on the area which you are cooling. Whereas in case of heat pump, you are concentrating on the area which you are heating. Okay. That is the only difference between heat pump and refrigerator. So these things, this diagram gets reversed in case of refrigerator or heat pump. So you will have again you have the source, you have the sink, then this is your working substance, and this line will get reversed. This line will get reversed. Very important. This is the line gets reversed, and instead of getting work, you are doing work. You are doing work. Okay. So in case of refrigerator, this is your refrigerator. So refrigerator interior, the volume, inside volume of the refrigerator. Okay. Whereas in case of heat, so this is your, again this is your Q2, this is your uh, Q1, and then this is your work done. Okay. So this is the refrigerator. In case of refrigerator, you are concentrating on the interior of the refrigerator. And in case of a heat pump, like suppose you want to heat a portion of your building, so you are throwing away some heat on this. So this part, so this part can be considered to be heat pump. Okay. So in case of heat pump, where you are throwing the heat, that is important. There you are concentrating. In case of refrigerator, from where you are taking the heat, that is important. Okay. So the Q2 that you are taking is important in case of refrigerator. Q1 that you are giving to the room that you are heating or area that you are heating, that is important in case of heat pump. So we have corresponding to efficiency, we have talked about. So these all these heat pump, refrigerator, engine, all are as per first law of thermodynamics or conservation of energy. Okay. So like your efficiency, and there is a corresponding term in a refrigerator and heat pump, that is called COP, COP, or coefficient of performance. Okay, that is called coefficient of performance. So coefficient of performance, what is that value? Coefficient of performance. That coefficient of performance is nothing but uh, that value is like that is a reverse. Remember, that is reverse, because in engine you want work done. Okay, but in refrigerator and heat pump you are measuring the heat that is extracted. That is your intention. Okay, work done is not your intention. The heat that is extracted from the refrigerator interior volume, that is your intention, right? Or the heat that is being thrown to the heat pump, that is your goal. So the what is your goal, that becomes the numerator. Okay, so it can be so it can be so your work done is your input. That has to be always in the denominator in case of refrigerator or heat pump. But either Q1, So either Q1 either Q1 or Q2, either of them are going to be uh, either of them are going to be okay. So either Q1 or Q2. So in case of refrigerator, it is Q1 by W. In case of this is COP heat pump. Okay, COP heat pump is equal to Q1 by W because Q1 is coming here, Q2 is coming from here. So COP heat pump is equal to Q1 by W. Similarly, COP refrigerator fridge is equal to Q2 by W. So remember always because uh, because uh, uh, your intention in refrigerator or heat pump is either Q1 by Q2. That is the intention. That is the goal. That's why that has to be in the numerator. Work done has to be in the denominator. Right? Clear? Clear? Yes. So this efficiency can never be equal to 1. Can never be, always it will be less than equal to 1. That is the first law of thermodynamics. You have to reject some of it. Similarly, as you know, this Q1 or Q2, these are going to be more than W. It has to be more than W because you know heat has to be less than W because you are converting heat into work. So heat cannot will be always more than W. Right? So this Q1, at least this Q1 will always be more than W. So this COP can it. So what second law of thermodynamics said? Without doing work, you cannot extract heat. You cannot throw away heat without doing work because you are going from a lesser temperature T2 to T1. So T1 is greater than T2. So you cannot transfer heat from a lesser temperature scene to a higher temperature source without doing some work. Not possible. The law of nature is transfer of heat from higher temperature to lower temperature. But if you are transferring heat from lower to higher temperature, you have to do some work. Okay. So that work can never be equal to zero. Work can never be equal to zero. So if it is never be equal to zero, that means COP can never be equal to infinity. So COP cannot be infinity. That is the with respect to heat pump or refrigerator. That is the statement of second law of thermodynamics. One is Kelvin Planck statement, which is related to heat engine. Efficiency can never be equal to 1. Another is Clausius statement, which is COP can never be equal to infinity. Okay. Uh, okay. That is one is Kelvin Planck statement, and another is Clausius statement. Some questions can come on that. Okay. Then so that is we have covered first law, second law, and the different devices which are operating as per second law and a first law and a second law. So first law helps us to derive the efficiency and coefficient of performance. Okay. So these are the formulas you have to remember because nowadays you are not deriving like the earlier classical days when we used to derive everything like we used to have long type questions of 16 marks. We used to derive the complete Carnot cycle efficiency. For that, we must know what is the and we used to get some. 10 mark questions on derivation of work done in isothermal process, derivation of work done in isobaric process, isochoric process, adiabatic process. What is that? So complete derivation you will to write, but because yours will be mostly MCQ mode, you should remember the formula. Remembering formula is very, very important. So at the end of the derivation, what you got, that needs to be always remembered, okay, for MCQ mode. Okay. Then after discussing like Kelvin Planck statement is telling no process is possible whose sole result uh, is the absorption of heat from reservoir and complete conversion of heat into work. That's the Kelvin Planck statement. Similarly, Clausius statement is related to a refrigerator. That also you can read and remember. It may come also. So after doing all these things, we have discussed about Carnot engine. So at the end of it, we found that Carnot engine efficiency is equal to 1 minus T2 by T1. Okay. So this is your source, this is your source, this is your sink. Source is at temperature T1, sink is at temperature T2. This is your working substance going through a cyclic process. This is your heat taken. This is your heat thrown away. This is your work done. So we have done that 1 minus, like we have done like W by Q1 in the efficiency. So this W and other things, after simplifying all these things, we have derived the efficiency of Carnot engine is equal to 1 minus P2 by T1. Very, very important to remember. Efficiency of a Carnot engine is equal to 1 minus uh, 1 minus T2 by T1. Okay. So there are some other things you also should remember, like Q, if when Q is greater than 0, that means heat is added to the system. Heat is added to the system. Added to system. Okay. When Q is less than 0, heat is taken away from system. Taken away from system. Then when del W is greater than 0, work done on the system, work done by the system on the surrounding. Okay. So work done by the system. Work done, work done by the system. By the system. On surrounding. On whom? On surrounding. Similarly, del W greater than 0, work done on the system. So, I was telling you have a piston cylinder arrangement. So, when this piston is moving forward backward, so this piston is connected to a connecting rod and then it is connecting to your shaft and in turn connected to the wheel. So when this piston is, it is the extreme position is here. So when it gets expanded, it does work on the system. Okay, when it is getting expanded. But when from here to here, when it is moving, this is your stroke of the like stroke length of your engine. Okay, and there will be some clearance value. Okay, so the compression ratio, there is something called compression ratio. It is the total volume. Like this is actually called your clearance volume. Okay, so this clearance volume, and then this is called swept volume. Okay, so compression ratio, there is a term called compression ratio in any engine, okay, like petrol or diesel engine. Compression ratio is nothing but volume before compression divided by volume after compression. So swept volume plus clearance volume divided by clearance volume is your compression ratio, right? So in any engine, in petrol engine, the compression ratio is less, like 5 to 6 or so. But in diesel engine, the compression ratio is more, some 20, 12, 13. That's why in diesel engine, and because of very high pressure, the temperature rises to such an extent that you don't have to put a spark to initiate the combustion. So in diesel engine, there won't be any spark. Because of high pressure, automatically if you inject fuel into it, the combustion will start. So you won't find a spark plug in diesel engine. But in petrol engine, you have a spark plug because the compression ratio is less and the temperature is not high enough to initiate combustion on its own. So we are telling about CI engine. This is a compression ignition engine. Why it is compression ignition engine? That means you are compressing it to such an extent that without spark it will create combustion. And petrol engine called SI engine, spark ignition engine. Your compression ratio is not that high, so you are putting some spark. So we are told about this is very important. All these terms. Q greater than 0, you are taking heat. Q less than 0, Q greater than 0 means heat is added to the system. Q less than 0 means heat is taken away from the system. Del W greater than 0, work done by the system. Del W less than 0, work done on the system. Okay. So uh, these things always this has to be remembered. There can be a number of numerical using this formula, and always remember that Carnot engine is the Carnot engine is the most ideal and efficient engine. There can be no engine which will be more efficient than Carnot engine because in Carnot engine we have assumed that all processes are reversible. The working substance is ideal gas. There is no dissipation of heat and it's a reversible process. That's why all four processes are quasi-static. Okay. So so we have done that a Carnot engine, the processes are like this. Okay, so this is P, this is V. So we can, the corresponding diagram, that is the TS diagram, that's the corresponding diagram, which is the TS diagram for Carnot cycle is nothing but, like I was explaining that day, this is T, okay, this is S, okay. So, so you are giving like that. This is the first to second. Okay, this is second to third. This is third to fourth. So you can see because from 1 to 2, 1, 2, 3, 4. So 1 to 2 temperature remains constant, right? So if temperature remains constant, this will become a horizontal line. And in a adiabatic process, S remains constant. S is called entropy. So entropy is order of randomness. So entropy remains constant in case of adiabatic process. So in isothermal process, temperature remains constant. In adiabatic process, entropy remains constant. So that's why that becomes a vertical line. So the area under TS curve is your net heat. The area under PV curve is equal to your net work done. And you know net heat is equal to net work done in a cyclic process because there is no change in internal energy. So if you think like this is my total area, so this is my Q1 and this is my Q2. So this net Q1 minus Q2 is equal to the area under this rectangle. Okay. So if you see initially the area under complete rectangle Q1 is this. The second area under rectangle is this. So when you subtract from this big area, this small area Q2, big area is Q1, small area is Q2, the resulting rectangle is Q1 minus Q2. Okay. So that is the, like, for a PV diagram, you have to remember the Carnot cycle PV diagram and corresponding TS diagram. It is not there, but just remember, like you to relate, like Q1 is Q is equal to T into delta S, right? So that is heat, okay? And uh, So now we'll study about coefficient of volumetric expansion. Okay, heat supplied in a system, delta Q, and what is the unit, and symbol, unit, dimension. Okay, so so as I said in physics, it is very important to know the dimension. Okay, so here they have summarized some of the dimension. The heat supplied is equal to del Q. What is its unit? What is its dimension? Dimension. So your heat supplied has unit of joule. Joule. Joule is nothing but force into distance, right? Force is nothing but mass into acceleration, okay? And then it is distance, right? Then mass, your mass is this. So if you see the unit, what it will be, mass unit is kg. Acceleration, you know, meter per second square, okay? Because velocity is meter per second. Acceleration is rate of change of velocity. That's why meter per second divided by second. It becomes meter per second square. And then your distance is meter. Okay. So it becomes kg meter square, kg meter square per second. This is your unit of heat supply. Okay. Or its dimension will be kg is meter, kg is mass. Okay, meter is nothing but your distance, or L square divided by T square, or otherwise you can write m L2 T to the power minus 2 is the dimension, and uh, kg meter per second square is your unit, or you can say joule is your unit. It can be simplified like this to find the dimension at the end. Okay. Then thermal conductivity we have already found out while studying the heat transfer in conduction mode. We have found out what is thermal conductivity. Yeah, as you remember, like del Q is equal to K A delta T divided by delta L. Right. So that is thermal conductivity. Uh, that dimension also you can find out. Okay, so like you have a rod and you have length L and descent temperature T1, descent temperature T2, then how much heat is transferred from end 1 to end 2, so that you can find out. The uh, unit and dimension of thermal conductivity. Okay, so that's how we have summarized what we have studied. So I hope with this you should be able to solve some numericals. Maybe in the next class we'll discuss some numericals, two, three numericals, one related to heat engine, one related to refrigerator, and one related to Carnot engine. So, and one related to work done for an individual isothermal process, individual adiabatic process. So at least five numericals. One numerical related to work done in isothermal. One numerical related to work done in adiabatic. One numerical related to Carnot engine. One numerical related to heat pump. So if we solve five, six numericals related to this, and the concept like area under PV diagram is equal to work done. So that concept can be used to solve many numericals also. So using at least one numerical for each of the five different concepts will give you better clarity. Okay. We'll discuss few numericals in the next class. Okay. Fine. Thank you.